So as I said, once that for each project alternative you define the utilities, then you can just compute the sum of the utilities. And this is, of course, valid, again, if each criteria is equally important. Instead, if you deem that you feel that you should give more importance to a particular criteria, then you could introduce weights. Yeah. And weights, introducing weights means that you are giving more weights, you get a weighted sum at this stage, and you give more weight to the criteria that is more important. Ideally, by definition, weights should sum to 1. By definition of weights. It doesn't change really your result if the weight don't sum to 1. But once that you introduce weights, it's better that you make sure that they sum up to 1. So in this case, you have 3 weights. It's better if you select the weights so that they sum up to 1. Now, the next question is how to determine these weights. So this is the subject of today's lesson, today's lecture. How to determine these weights. And of course, you can determine the weights by subjective identification, like I feel that the economical benefit has the priority and therefore I give a weight of 0.4, and then you may have like environmental flow requirements, so the utility associated to the environmental flow that you release downstream, and you may say, yeah, it's important but not at the economical value, and therefore I give a weight of 0.2. And then for the third, you may have, for instance, the noise, because sometimes if you, for instance, realize an hydropower plant, it's noisy. So some people don't really like if it is too big, because if you take too much water, then you need to increase the size of the turbines, and therefore you increase the noise, so people may not like it. And you may say, okay, this is important, because if people don't like it, so the third weight could be, again, 0.4. So this is subjective judgment, and this is an opportunity. But, you know, when you have to reach a compromise among many stakeholders, then it becomes a bit difficult. Because, of course, if you ask one people, he would say that economical benefit is the best thing, and he would give like weight 1 to the economical benefit. Other people would say, no, I'm not interested in the money that you get, but I'm interested in saving the environment, and therefore the other people may give weight 1 to the environmental flow. And so, you know, this is a difficult choice. And it's also a difficult choice sometimes to identify the utility function. So basically, in decision theory, people started to think about solutions for solving these problems. And therefore, I'm introducing to you today an option, which I think is interesting in water resources management, much interesting, with some practical applications already. And what I'm introducing today is called pairwise comparison. And in Italian is confronto a coppie. And I make available on my website today only some supporting material that I will use to explain to you this pairwise comparison. And let me say what is the basic idea. The basic idea is that when you have to compare different solutions, more than two alternatives, the comparison becomes a bit tricky. Because if you have to compare two solutions, like take water or not to take any water, it's easy to choose. When you have three, which could be not to take water, take a certain amount of water, or take a higher amount of water, then you get in doubt, because it's relatively easy for the human brain to make a comparison between two alternatives. When the number of alternatives increases, then it becomes more difficult for the human brain to make a relative comparison. The judgment becomes more subjective. And therefore, the idea is to split the evaluation of more than two alternatives in a sequence of evaluation of just two alternatives. Again, the idea is to split the evaluation of several alternatives in a sequence of evaluation of two alternatives. This is the reason for the term pairwise confronto a coppie, meaning that any time during this sequence of evaluation you have to evaluate two alternatives only. So let's have a look at the supporting material that I uploaded today. Let's see if we can get to... You don't mind if I turn the light off, okay? I think it's a bit better in this way. And you see that there is a pairwise comparison here. Now I download the file. And let's see it. There are some files here. Okay. So first of all, there are 4 files, and first there is an example of application. This is written in Italian. So it's an example of application for designing an hydropower plant, a small hydropower plant. And this is written in Italian. You don't need absolutely to read it, but I just wanted, given that I have this this information available, which is a nice example, I wanted to make you available, to make it available to you. Now let's now turn to instead the real supporting material, and this is a printout from a Wikipedia page. And basically, if you look in Wikipedia and you look in English, you look for pairwise comparison, then you get to this page, which you can download from my website, but it's in Wikipedia. And basically, this is an example of application of pairwise comparison, which fits to our purpose. Of course, doesn't refer to water resources management, it refers to the choice of the best leader for a company. But I think it is very useful. And also you have another file, which is the solution for the example, and I will make reference to this. So basically, this is just an example that I would like to solve with you. Sorry, do you have a question? No, no, sorry. And I feel that really it fits to our purposes. And let me clarify that in this case, this example is also a bit conceptually different, because we have 2 problems here. First of all, the problem is the selection of a leader. And you see here the description of the 3 persons. Of course, this is a fiction. And basically, we have the criteria selected by the company for the identification of the leader, and the criteria are, you see in yellow here: experience, education, charisma, and age. You see there is written goal, choose the most suitable leader. For us, the goal could be, for instance, estimation of the river flow withdrawal. And then there are 4 criteria. And the 4 criteria, in our case, could be like economical benefit, preservation of the environment, a reduction of the noise, and another one could be, for instance, minimizing the length of the river flow interested by the withdrawal, because usually when you produce hydropower, you get the water from the river and you release the water downstream. And you have the option of releasing the water soon, but in this case you reduce the jump, and therefore you reduce the amount of energy that you can get from the hydropower plant, or you can release more downstream. So this could be our criteria. And then you have the alternatives. And you see the alternatives in this case are just 3. And it's better to limit to 3 alternatives because it's easier to understand. And in this case, the alternatives are a finite number. In general, we may have infinite alternatives, as I said. But of course, if you want to make a pairwise comparison, you have to reduce the number of alternatives and the number of criteria, because if you have an infinite number of criteria and an infinite number of alternatives, you can't apply pairwise comparison. And therefore, if you want to apply this method, it's better if you just limit the number of alternatives and criteria. This is always possible, because let's say that the case in which you have an infinite number of alternatives is a virtual case. Because even if your decision variable is the river flow withdrawal, which means that you have an infinite number of alternatives, you can split the range of possible withdrawals in a finite number of intervals. And for the practical need of design, this is always possible, because you don't need to define your water withdrawal with like 1 million digits. If you limit to just 1 digit may be enough, which means that you limit your number of alternatives to a finite number. So let's concentrate on this case then, where we have 4 criteria and 3 alternatives. And in our case, here we apply, in the case of this example, pay attention to this difference with respect to the case that I introduced there. In the case of this example, we use the pairwise comparison not just for determining the weights. So not just for determining the weights of each criteria. This is the problem from which we started there. I have the criteria, I said, I already have my utility function, and I want to determine the weights. In this case, pairwise comparison is used to this end, to this purpose, but in this case, the pairwise comparison is also used to determine the utility function. So, to determine what is the utility of each alternative. Okay. So, having said that, let me start with this first step to determine the utility of each alternative, the numbers that are in that table. And then we will move to the determination of weights. Fine. So, let's focus on this example. Again, it's on Wikipedia. 4 criteria, 3 alternatives. The 3 alternatives are the 3 guys, Tom, Dick, and Harry. And the criteria are experience, education, charisma, and age. Good. Now, let me introduce pairwise comparison. Pairwise comparison, in general, as I said, means that you compare 2 things at a time. Each time you compare 2 things. And therefore, you are asked to judge among these 2 things what is the more important. And you are required to express your judgment using a number. So, look at this table. Intensity of importance. 1 means equal importance. So, if you are asked to evaluate what is more important, economical benefit or preservation of the environment, you may say 1 means the same for me. 3 means moderate importance, which means that if you give 3 to the economical benefit, it means that with respect to the preservation of an environment is moderately more important. And be careful, this means that if you are asked the opposite question, what is the importance of the environment with respect to the economical benefit, you should give a consistent answer. So, if I say that this is benefit and this is environment, I give 3 to this, and remember that 1 would mean equal importance, then it means that you have to give 1/3 to environment with respect to the benefit. So if one asks you, what is the importance of benefit with respect to environment, and you say 3, then if the next time one asks you, what is the importance of environment with respect to benefit, you should say 1/3. And of course you would say obvious. Why are you saying this? You will see in a minute that it's not so obvious. So you see this scale. 5 is strong importance, 7 is very strong, 9 extreme. So you have, by definition, 5 options. Of course, any number in between is fine. You may say 4.1. But usually these numbers are used. This is just by definition. Okay. Now let me introduce why it's not so obvious to be consistent. Let's suppose that you have 3 criteria. Benefit, economical income, and noise. Okay, fine. Then we cannot compare the 3 of them. We want to make pairwise comparison. So let me compare benefit and economics. And we said, okay, 3, 1/3. Then I have to compare benefit with the noise. So benefit, noise. What to say? Let's say 5, which means 1/5. And then the next comparison is environment and noise. You have to be careful here. Because, you know, the benefit is 3 with respect to the environment, and it's 5 with respect to the noise. Which means that implicitly you are assuming that the noise is less important than the environment. And therefore, if you put here that environment is 1/3, and this is 3, this is not consistent. And if you have 10 of such evaluation, of course, it's not easy to be consistent. But this is a nice feature of this method. Even if you are not consistent, it tells you something. The fact that you could be not consistent is an indicator that this decision is not so easy. This analysis is not so easy. Because if I ask you what would be the correct answer here, you have to think a lot. Basing on the first two answers, to define the third one, of course, environment is more important than noise, but what would be the correct answer? Okay, so you see a potential problem already. Okay, very good. Let's go back to our personnel selection problem. And here you see the curriculum, the CV, and let's not focus on the details. Just you see here some elements for the evaluation, for the pairwise comparison, In your case, you will have any technical details of your alternatives, and you will have any information, any possible information on the river, the environment, the people, the society, etc. Now, let's move to the first criteria, experience. And now our aim is to give a score, the utility, I erase the utility, to each alternative based on the first criteria. So in the table here, you are moving in this direction. I concentrate on a criteria, and I have to give what I call here utilities. In this case, they are not utilities. They are just simple weights to the three alternatives. In my case, they were utilities. In this case, they are weights. Why they are not utilities anymore? Because, you know, the utility function, it's defined accordingly to some definitions, like the utility should be an increasing, not decreasing value with respect to the real variable, and the utility is defined over a real variable. You can also define the utility over discrete variables, but you know, in this case, we are just defining weights, and we cannot call them utilities because it doesn't really meet our definition for utility. Okay, so you see here an example of evaluation, like Tom with respect to Dick is 1 1/4, and then you have 4 and 1 between Tom and Harry, and 9 and 1 with respect to Dick and Harry. So really, and you see in the matrix here the translation of this first assessment. So you have this first assessment, so if you assign to Tom the value of 1 and you say that Dick is 4, then this means that basically you see here Tom with respect to Tom is 1, of course, the same importance. Tom with respect to Dick is 1/4, and Tom with respect to Harry is 4, because you see that in the second row Tom with respect to Harry is extremely important. You see a difference here because they didn't put the inverse of each score in the other candidate, because this is just a first evaluation in which one says, okay, I start from Tom, and what is the importance of Harry with respect to Tom? Is 4. Okay, then if you accept this evaluation, then in the table you have to put that Tom with respect to Dick is 1/4. So basically, this is the matrix that you have to look for. And this matrix, which reports the results of the pairwise comparison, is in this case 3 by 3, because we have 3 candidates. And we refer to the first criteria. If we had 4 candidates, it would be 4 by 4. And along the diagonal, you have always 1, because you are comparing the person with the same person, and then you get 1. So let's look at this, because this meets the definition that I gave. This introduction is a bit misleading, because you know I wouldn't put 1 there. I would put 1/4. Is it clear so far? Okay. Now the problem, let's move forward. Now we can define the priority. You see, here I have the 2 matrices, and here there is the priority. So question, how did they compute the priority? There are many ways. I tell you one way, which is simple, which is not the way that was used here. Because basically, here what they say, and I understand that what I'm saying now is a bit difficult to understand. I am aware of this. And I'm just want to mention to you what is, from a mathematical point of view, the most correct solution. You have a matrix, and the values that you get here, mathematically speaking, they are the values in the matrix right eigenvector. In Italian is autovettore destro. So I understand that you probably don't remember what eigenvalues and eigenvector are. Maybe that I am underestimating you. If you remember what autovalori and autovettori, eigenvalues and eigenvectors are, this is fine, perfectly fine. But in my case, I have to go back to my background and look what is. And I want to avoid these mathematical details. So basically, you can take the right eigenvector and you get these values. But there is, to me, an easier way to get another estimate which is very close. It's not really the same, but it's very close. And I would say that if the matrix is consistent, we get the same solution. Given that there is some inconsistency here, of course, they differ a bit. So let me explain to you the simpler way. Get these columns and take the sum. So for instance, for Harry, you have 9 plus 4 plus 1, it's 14. And then for the other, you get the sum of all the columns, and then you get the sum of the sum, which means the sum of all the elements in the matrix, which is about 20 in this case. Fine. Then in any row, you get the sum of 1 plus 1/4 plus 4, and you divide by the overall sum. So this is 5 plus 1/4. The sum in this row is 5 plus 1, 5.25. If you divide by 20, which is the overall sum, you get close to this number. So in any row, you get the sum, and then you divide by the overall sum. In this way, you get 3 weights which sum to 1, by definition, of course. Because if you divide the sum in each row by the overall sum, in each row you get numbers, 3 numbers, that sum up to 1. And then you get the weights of each candidate, Tom, Dick, and Harry, with respect to experience. The evaluation of each candidate with respect to experience. Look, the matrix is not really consistent. Because if you look at these evaluations, and therefore you see that Dick is 4 times Tom, Dick is 9 times Harry, and then you see that Harry is 1/4 Tom and 1/9 Dick, there is some inconsistency. And therefore, how can we detect the inconsistency? Let me postpone this. Okay, you see that under each matrix there is a measure of inconsistency. I anticipate to you that if this coefficient is less than 0.1, the inconsistency can be tolerated. Because if your evaluation is highly inconsistent, then of course cannot be tolerated. But if it is the inconsistency is small, you can tolerate it. And I will explain you in, let's say, 5 minutes how to compute this number. It's a purely mathematical computation. Now, the example moves forward with the evaluation of education. You see? Education. Second criteria. Let's move forward with the evaluation of the charisma here. these matrices are symmetric, always. Just if you think about how they are constructed, they are symmetric. Because, for instance, let me look. This 5. 5 is Harry versus Tom. Okay, now let's go in the symmetric element. Is Tom versus Harry. So, sorry, it's not symmetric, it's antisymmetric. I think it's the correct terminology is antisymmetric when you have a matrix where you have one in the diagonals, and above the diagonals and below the diagonals you have the reciprocal of the numbers. I think it's antisymmetric, but in any case, I hope you understand what I mean. Okay, fine. Now we get to the second issue. At this stage, we have for all the criteria, 4 criteria, the evaluation of the candidates. Now we have to put the criteria together. Determination of the weights. So it's our case. Now the pairwise comparison is more complicated because the criteria are 4, not 3. So we have to perform 6 pairwise comparisons. So basically, you see here the evaluation. Experience versus education, 4. Experience versus charisma, 3. Experience versus age, 7. Education versus charisma. Charisma is 3. Education versus age, 3. Age versus charisma. Charisma is 5. Question, is this evaluation consistent? Who knows? And you see the explanation, because one important issue in this kind of evaluation is transparency. So you should always explain in a few sentences your consideration. Now we have to determine the weights based on this evaluation. Let me move forward. This is the matrix. The weights are determined, as I said to you before. Eigenvector, or in a simpler way, you take the sum in each row divided by the overall sum. There are other suggestions, and you have to look at the inconsistency. So basically, we still have the open parenthesis of the inconsistency, but basically we are at this stage, we are done. We have the evaluation of the candidates for each criteria, and we have the weights. So let's take the final synthesis, and here it is. So basically you have for experience, the first row is experience, and then you have the 3 candidates with their evaluation and the weight. You see? 3 candidates. Let's refer first row experience. The 3 candidates, these are the scores that they got with respect to experience. They sum to 1, and then we have the weight of experience. So basically, these are the 3 weighted scores of the candidates, which of course sum up to the value of the weights of the weight. And then you can perform the same computation for education, which has a weight of 0.127, for charisma, which has a weight of 0.27, and then the age, which has a weight of 0.056. And of course now for each candidate, you have to make the sum of these numbers. Here you see the result. Tom, experience, education, charisma, age, 0.358. Dick, experience, education, charisma, age, 0.5492. And then Harry, their sum is 1, by definition. And so you see that the best candidate is Dick. And this is indeed an example of a very objective evaluation in which we try to decompose our quite complex problem, 3 candidates and 4 criteria. We decompose the complex problem in a sequence of simple comparisons. And if you try to reach the same result at the beginning by just doing a perceptual evaluation, you probably wouldn't find the same outcome. So I think this clarifies how to compute the weights in a multi-criteria problem by using pairwise comparison, and also it clarifies how, in some cases, and especially when you have a finite number of alternatives, you can use pairwise comparison to assign utilities to each alternative with respect to each criteria. Now there is the problem of consistency, and it is treated here in a way that is not really satisfying to me, and therefore it's better if we refer to another file that I included here, which is this file called consistency PDF. And let me see. First of all, from the evaluation matrix, you remember that we had, for instance, for the weights, a 4x4 evaluation. You can compute, again, I understand this is not simple, the eigenvalues autovettori. Then you can get the maximum value of the eigenvalues. It can be proved that if you had a perfectly consistent matrix, the maximum eigenvalue would be equal to n